Now we will introduce a very famous dynamic programming algorithm in solving this type of a problem. To solve a dynamic programming problem, typically the problem needs to be decomposable. The decomposable means the entire problem can be decomposed into multiple parts. We solve the entire problem, so each subproblem has to be also optimum. So that indicates that the optimality of the big problem is equivalent to its optimality of subproblems. How to understand this concept? A very famous example for dynamic programming, it is a shortest path problem. Consider you are starting from one city A, and then your destination is another city B. In the middle, there may be several intermediate steps. So there are different paths you can choose from A to B. And then your goal is to try to find the path with the smallest distance. We can immediately see that if a certain path from A to B is the optimum path, that means the shortest path, then we immediately know that from the path C to D to B, it is a part of the entire path. So the distance of this part should be also the shortest path from C to B. The reason is very straightforward. For example, if you have another path which is smaller, the entire path from A to B can be updated with A to C and then C to B with the shortest path. Then this path will be the optimum path, so which is contradicting with our assumption. That is why we call this problem decomposable. So when the big problem reaches optimality, then each subproblem has to reach its optimality at the same time. So let's see how can we decompose our problem for the one-to-one system. So our decision is when to dispatch the vehicle. So let's see, this is T0, T1, and then T2. Our objective is to minimize the area, and together with this fixed cost. Every time you dispatch, there is a fixed cost. This problem actually is decomposable. Consider it's a subproblem. If we're starting from T1 and then to observe the rest of the problem, we can see that the demand curve is truncated. We only focus on the demand curve from T1. And then there are one dispatch from T0 to T1. So suppose that T0, T1, T2, this is optimum solution to our problem. And then if we consider this subproblem starting from T1, so this is a subproblem T1, then we can immediately tell that the schedule T1, T2, this is optimum solution for the T1 problem. So this is very intuitive, right? So if you have another solution, let's see if there's another T2, if T1 to T2 prime is optimum for T1 problem, and then the total cost starting from T1 to T2 prime, so that means this cost, and then with this shaded area will be smaller. You can see the rest of the part from T0 to T1 is the same. So that can tell us that the total cost can be adjusted such that T0, T1, T2 prime will be the optimum solution. That validates our assumption, right? This is our assumption, so this is contradicting. So in this sense, our problem can be solved using dynamic programming. Now let's look at how we use dynamic programming. Follow what we just discussed. Let's decompose the problem into two subproblems. We call it a one-step problem plus the rest of the problem. Okay, because in general, we don't know how many dispatches are optimal. In our shooting method, we enumerate all possible dispatches. Here we can embed the decision for dispatches together in the dynamic programming structure. For example, here T0, which is actually given by this problem, T1 is our first decision of the schedule. So from T0 to T1, there's a new vehicle dispatched. We call the problem from T0 to T1. This we call it one-step problem. And then from T1 until Tmax, there may be multiple dispatches. For example, T2, T3, T4, blah, 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 right? We don't know how many dispatches are optimum. Then we can wrap up all the problem starting from T1 to the end. Write the subproblem from T1. So let's see what is the total cost. We can see the total cost, including the transportation cost or fixed cost, plus our holding cost. So let's see this cost. For this one-step problem, we have one shipment cost. This is a fixed cost. And then we have this shaded area, which is related to our holding cost. So we have the cost for the one-step problem to be, let's call this area I1. Okay, and then we have the cost for the subproblem T1, which is not clear now because there are multiple dispatches. So the issue is that if we know what is the optimum cost from T1, if we know what is the total cost of the subproblem T1, then we can calculate this total cost by just sum the cost for the one-step problem and the cost for the subproblem starting from T1. So in general, if we want to calculate the total cost of the problem, we can construct a problem called subproblem T0 because the problem starting from T0 is same as the entire problem. And then this subproblem T0 can be equal to a one-step problem from T0 to T1, and we can have this subproblem from T1. So the issue is that we are not sure about if our first decision should be T1. What is the optimum value of T1? So in this case, we need to find the minimum because we want to minimize the total cost. We want to find the minimum value of all possible T1. This structure, we call it Bellman equation. So that indicates that a dynamic programming problem can be decomposed into its one-step problem and then the rest of the problem. So you can see there's a very interesting definition. We have a repetition within the definition. The only difference is the parameter is different. T0 means the starting point for this subproblem starts from T0, and T1 in the parameter means the starting point for this subproblem is T1. That means that if we know the optimum solution of the subproblem starting from T1, then we can further solve the optimum solution for the subproblem T0 by enumerate all possible T1. So in reality, enumerate all possible T1 is difficult. We should typically discretize T1. So after discretize the problem, then the possible T1 can be chosen from this point to even Tmax. Any point within this range can be T1. So for example, if we choose T1 here, given the demand, that indicates our first dispatch will be on T0, and then our second dispatch will be on T1. And then we are not sure about when to dispatch next. But if T1 is at Tmax, then this is easier. We will just have one dispatch and pay all this holding cost. So if T1 is in the middle, T1 is here, then we'll just dispatch based on our T1, and the rest we don't know yet. So in reality, to know the optimum solution of the subproblem from T1, we'll do a backward search. For example, first let's see T1 equals to Tmax. So when T1 equals to Tmax, we have just discussed, you only have one dispatch. So your one-step problem could be from T0 to Tmax. And then your subproblem is from Tmax. And then here, this is very interesting that if we want to find out optimal solution for a subproblem starting from Tmax, the solution is immediately known because there's no need to dispatch anything, right? So we can know that the total cost is 0 and then no dispatches, or we can just call the dispatch time as Tmax. Now let's see if T1 equals to Tmax minus 1, or this 1 unit. Here we assume the discretization step is 1 without loss of generality. So if T1 is Tmax minus 1, You have, this is one dispatch, this is another dispatch. So we have a one-step problem from T0, T1, then plus the subproblem from T1 or Tmax minus 1. So let's focus on the problem from T1 to Tmax. We take this part out. You can consider this is a one-step problem from T1 to Tmax. There's no much choice. You have dispatched one vehicle at T1, and then the next possible decisions are only Tmax. So there's no other possible ways to decide your next dispatch. So this is the only decision you can make. Then if we calculate the total cost from this one-step problem, T1 to Tmax, then the subproblem is solved. Now let's consider our subproblem from Tmax minus 2. So let's see our figure. Let's simplify Tmax minus 2 minus 1. You see this is our demand. So as you can see, our decision for T1 can be either here or so. That indicates you will find the minimum of these two decisions. So the second case, this is just one-step problem from Tmax minus 2 to Tmax. And the first case is, this is a summation of one-step problem from Tmax minus 2 to Tmax minus 1 plus the subproblem from Tmax minus 1. So here we already solved the subproblem from Tmax minus 1. So we can find out the total cost for the two cases, and then we find the minimum one. So our third case, the subproblem Tmax minus 2 is solved. And then we can keep doing this until the n plus 1 step. We want to solve subproblem of Tmax minus n. And this problem can be decomposed to the one-step problem from Tmax minus n to Tmax minus something in the middle, and then plus the subproblem. Okay, so that means, okay, and then it is a subproblem from Tmax minus I to Tmax. Because we solve the subproblem from Tmax to the left, so that indicates this subproblem from Tmax minus I has solved. So we can find out the minimum value for different I, and then Tmax minus n is solved. So keep doing this until finally we solve subproblem. When we solve subproblem T0, all the problem starting from the right-hand side of T0 has been solved. So that means T0 plus 1, subproblem from T0 plus 1 is solved, T0 plus 2 is solved, until Tmax is solved. So we have solved all the subproblem starting from T0 plus 1. In summary, let's just go through the backwards recursion process again. So first step, we solve the subproblem for Tmax, and then with the subproblem for Tmax, let's denote it by sub Tmax, and then we can solve the subproblem for Tmax minus 1. Solve it, we just calculate this one-step cost from Tmax minus 1 to Tmax. And then after this, we can solve the problem for Tmax minus 2. How to solve this problem? There are two cases. The first case is use this one step from T minus 2 to T minus 1, and then use this T minus 2, T minus 1, plus the sub problem from T minus 1. Or you can directly solve this step problem, one step problem from T minus 2 to Tmax. Okay, and then there are a lot of intermediate steps until you want to solve the subproblem T0. Then how to do it? You can jump to one step to T0 plus 1, or jump to t0 plus 2, or jump to t max minus 2, jump to t max minus 1, or jump to t max. When we solve the subproblem at each time step, we just compare all these paths and find the minimum one. So let's see an example. Still recall examples on our previous calculation. So this is 1, this is 2, this is 3, then the gradient 100, 80, 50. Easiest examples. Let's discretize the time horizon into 4 steps. Let's see all the possible time you want to ship belong to 0 or 1 or 2. So let's see, our CI is still 10 and our fixed cost is 189. So let's use C to represent the one-step cost. Use V to represent the subproblem cost. That's starting from backward recursion, right? So the first step, let's see the subproblem of Tmax, which is 3. So let's calculate the cost for the subproblem starting from time 3. As we discussed, it should be 0. There's no cost. So next step, let's do our subproblem from node 2. So let's see the cost for the subproblem starting from time 2 equals to the one-step cost from 2 to 3. Let's calculate this shaded area. So it has one shipment, so it has one CF plus CI times this triangle area. So CF is 189, CI 10 times the area. So the area should be 25. This gives us, okay. So now let's do subproblem starting from 1. So we need to compare the two cases. One case is we starting from 1 jump to 2 and then plus cost from 2, or we directly jump from 1 to 3. Okay, so 1 to 2, this is a triangle area of this triangle. Area is 40. This equals to 589. And then from 1 to 3, this is a triangle, a concave triangle. So this equals to, so the total cost 1089. So this equals to V2 is 439. This equals to, so we compare these two. This one is small. So we know V1 equals to 1028. So the subproblem from 1 to 3, the optimum solution should be 2 dispatches. The 2 dispatches is with cost 1028. The 1 dispatch will have the solution of 1089. Now let's solve the subproblem from 0. So that means we solve V0. We need to compare 3 cases from 0 to 1, and then we'll have our subproblem V1, or we jump from 0 to 2, one step from 0 to 2, and then plus our subproblem 2, or we directly jump to the end. So let's calculate C01. This is times the triangles. This gradient is 100. So this equals to 50. And then from 0 to 2, then this is concave triangles. This is 100. This is 80. Is equal to, now we have the one-step cost from 0 to 3. So this is a big triangle with 3 parts, equals to the first choice. We have solved V1 to be 1028. In the second case, we have solved, we also know V2. And then we know the third choice. Okay, so compare 3, we know like 1717 is the smallest. smallest cost. So that indicates that we should dispatch a vehicle at time 0 and then at time 1. So this leads to our solution. So we know V0, this is our optimum solution. And we know V1, and we know V2. Okay, so this indicates our solution. From V0, V1, and V2. This is our total cost.